Continuing in 11.3, we are up to example 5. It wants us to work with the function f of x equals the cube root of 1 plus x, which means 1 plus x to the 1/3. Find the first 4 terms of the binomial series centered at 0. Okay, so I'm going to do the same thing I did a few minutes ago. C sub 0 is going to be your 1/3 taken 0 at a time, which is automatically 1. C sub 1 is going to be your 1/3 taken 1 at a time, which is 1/3 over 1 factorial, or 1/3. C sub 2 is going to be 1/3 taken 2 at a time, so that's going to be 1/3 times negative 2/3, 1 minus 1/3, 1/3 minus 1, over 2 factorial, which gives you negative 1/9. And then C3 is going to be 1/3 3 at a time, so that's going to be 1/3 times negative 2/3 times negative 5/3 all over 3 factorial, and you get 5 over 81. So I have my constants. So the binomial, or the polynomial, is going to be 1 plus 1/3 x minus 1/9 x squared plus 5 over 81 x cubed minus ... So that answered part A, which was just like part A in number 4. Part B, use part A to find the first 4 terms of the binomial series g. Now g is the function, the cube root of c plus x. So let's not start from the beginning. Let's just write out the individual pieces. We're going to fix this to say the cube root of, let's divide everything by a c. And then I could say that that would be the same thing as taking actually, I don't want to divide by it. I have to pull it out. Let me fix that. Pull out the c. Let's write it as the cube root of c on the outside, 1 plus x over c. But now I can pull the c out, and it would be the cube root of c and times the cube root of, oh, I lost my 1. There it is. 1 plus x over c. Which would mean that that's just the cube root of c times whatever f was, plugging in x over c. So all I have to do is take the f function now and plug in x over c. So my series for g turns out to be, now it's going to have this cube root of c out there. Then it's going to be a 1 plus a 1/3 x over c. Then it's minus 1/9 x over c squared, and then 5 over 81 x over c cubed, and then minus ... Now, C wants us to use part B to approximate the cube root of 23, the cube root of 24, all the way out to the cube root of 31. Okay, so what's happening is, if we look at the cube root of 23, and they actually didn't start with the cube root of 23, they decided to do the one in the middle. Okay, instead of doing all of these, I'm going to look at it as, if I look at the cube root of, let's just pick 29, that would be the same thing as the cube root of 27 plus 2. Now, if I'm trying to figure out what's going on here, this piece, the 27, would be the c, and the 2 would be the x. Because remember, it was c plus x. So we're going to let c equal 27 and x equal 2. Why are we picking 27? Because we know the cube root of 27. It's 3. So to find the cube root of 29, I would say it is the cube root of 27, and then 1 plus 1/3 the x over c, so 2 over 27, and then minus 1/9, that's a minus, 2 over 27 cubed, and then 5 over 81, 2 over 27. No, this was squared, not cubed, because here's the cube. And you put all that nonsense in your calculator, 3.0723. Now you have to do this for all of them when you do the problem. And in the book they have a chart showing you how far off it is. It's not far off at all. 10 to the negative 5 is pretty close. So I'm not going to do all of those. That's sufficient. The next thing they talk about is the remainder. You're going to have all these derivatives for your Taylor series, and the limit of the remainder has to go to 0 if you want to know that it converges. So the remainder, after n terms, would actually be the next term. If you chopped it off at the nth term, which is what I'm saying here, then the error is going to happen at the next term, which would be the n plus 1 derivative, evaluated at the number in question, over n plus 1 factorial, and then my x minus a to the n plus 1. And so that's what I'm going to work with in this section here. We're talking about when you truncate it, what's the remainder? And then the question is, does the remainder converge to 0? Sorry about that. Okay, so example 6 says, show that the Maclaurin series for e to the x converges for 2f from negative infinity to infinity. So we already figured out that that summation was k equals 0 to infinity of x to the k over k factorial, which we could write out. And so on. So the remainder would be e to the some number over n plus 1 factorial x to the n plus 1. And c has got to be somewhere between 0, where it's centered at, and x. So that means that we are between e to the 0, which is 1, and e to the x. So if we're trying to pick the biggest thing possible for my remainder to find how far off I could possibly be, e to the 0 is 1, and so e to the x would definitely be larger than 1, no matter what you stuck in there, because it's 2.7 to some number. So all I really have to do here is say, well, e to the x is the bigger of the two, so I'm going to say that the absolute value of r sub n of x must be less than or equal to e to the x over n plus 1 factorial x to the n plus 1. And now if I take the limit as n goes to infinity of this, of the e of the n plus 1 on the bottom with the factorial on it is going to make it get really, really large, and so that nonsense is going to end up going to 0, which means the whole thing is 0, because we're using the fact that x to the n over n factorial goes to 0 as n gets large, because remember, factorials always outstrip exponents. So since that remainder heads toward 0, then it makes sense that this thing converges for all x, and there's not a leftover piece because the remainder is heading toward 0. And the question is, if we want the remainder to be 0, if the remainder is 0, then it's converging for all x, from negative infinity to infinity, which is what they